The second lecture will on how we really compute it. So then from a previous talk, we know that we can model all the shapes and we can model the mappings between two shapes. Now the issue is how we really compute it, how we convert the abstract series to something concrete computational code. There's many methods. Then here we only focus on one method, which is called the surface Ricci flow. So the source code can be downloaded from my web page. So we say that this is the definition for conformal map, given mapping between two metric surface. Then if the pullback metric is proportional to the original metric, the difference is a scalar function, then this mapping is angle preserving and is conformal. We say that the conformal mapping has special properties, basically preserving infinitesimal circles and preserving odd angles. So if you put a checkerboard on a plane, then you pull back the checkerboard, you'll see all the right angles or checkers are well preserved. Okay. Then we say that the uniformization, arbitrary shapes can deform to three canonical shapes. So this lecture focuses how we really compute that. Then this is related to something called a Yamabe problem. Suppose we have a surface with a remaining metric. Then locally, we can build this isothermal coordinates. The remaining metric equal to E2 lambda UV, then the du square plus dv square. Okay. Then under this metric, okay, we can calculate Gaussian curvature. So the Gaussian curvature has a very simple form, okay, which is the Laplacian of the conformal factor. Okay. So here, there is a conventional Laplace operator on the plane. Then you put this term. Then this becomes Laplace Beltrami operator on the surface, determined by the remaining metric. Then the lambda, okay, is the conformal factor. Then this one gives us the Gaussian curvature. Suppose you deform the remaining metric by a conformal factor. This means you conformally deform the shape. Then how the curvature will be changed. So that's the problem. You deform the remaining metric by this way, then the curvature will change accordingly. So here, G bar is a new metric. Then the lambda is the conformal factor. Then the K bar is the new Gaussian curvature. K is the old Gaussian curvature. Similarly, we can calculate geodesic curvature on the boundary using this formula. Okay. Then the question is as follows. Suppose we want to deform the original remaining metric, okay, conformally, such that the Gaussian curvature equal to something we defined, okay, something we desire. So basically, in this equation, K bar is the condition we want to reach. Then the lambda is the unknown, okay. Then the G is the known metric. K is the original Gaussian curvature. So we want to solve this equation, okay. Then so we see that. So this equation is highly nonlinear, okay. We cannot solve it using conventional PDE method. We cannot solve it using such as finite element method. Then it's unclear whether we can solve this using a level set method either. So basically, this is our goal. Basically, give you arbitrary shape with an original remaining metric. Then we have a desired Gaussian curvature. How can you compute the desired remaining metric? Okay, so this problem is called Yamabe problem. So this is a 2D Yamabe problem. Then this can be generalized to arbitrary dimension. Then the existence, okay, and the uniqueness of solution has been proven in the literature geometric analysis. Okay, then one powerful way to solve this is proposed by Hamilton. So basically, in order to prove Poincare conjecture, Hamilton invented something called the Ricci flow. For surface case, the Ricci flow has a very simple form. So basically, we can see Gij is the remaining metric tensor. Okay, we flow the remaining metric tensor, okay, proportional to the current Gaussian curvature, okay, and with a constant term. So here, chi is the Euler number of the surface. A now is the total area at the very beginning. So this is a constant. Then this is called normalized, okay, surface Ricci flow. Then we can prove that during the flow, the total area doesn't change. So the total area is a constant. Then this flow will converge, okay, eventually the Gaussian curvature equal to constant everywhere. Okay, this was proven by Hamilton in 1982 for genus 1 and the high genus case. Then the Bancho later, after 5 years, proved this convergence for genus 0 case. Okay. Then for surface case, the Ricci flow is very special, which is conformal. So basically, at time t, the remaining metric can be written down as an initial remaining metric multiply conformal factor here. Then the conformal factor evolve according to this equation. Okay. Then what's the intuition behind that? So here we explain the intuition. Basically, we know the Gaussian curvature is the Laplacian or the conformal factor. Then we evolve conformal factor, proportional to the Gaussian curvature. So therefore, the evolution for the Gaussian curvature satisfies this equation. Then this equation, the major term is a heat diffusion. Okay, so this is a nonlinear heat diffusion. Then when times goes to infinity, we know the total Gaussian curvature is constant. Then the curvature function will become smoother and smoother and smoother, and eventually become to constant. So basically, that's the idea. We try to diffuse the curvature. Okay, so that's how Hamilton invented this method. Then this is a very powerful tool to solve Yamabe problem. So our goal is try to discretize the theory for surface Ricci flow, and then based on that, develop our computational method. Okay. Then we know that in engineering field, we represent the surface using triangle mesh. Okay. We have surface, we triangulate it. Then each triangle, we're using a small Euclidean triangle to approximate. Then, so basically, then we can also treat each small triangle as a hyperbolic triangle or spherical triangle. Okay, it's unnecessary to assume all the triangles to be Euclidean. But for simplicity, we only cover Euclidean triangle case. Then we need to generalize the concept for remaining metric. How can we define remaining metric on triangle mesh? How can we define curvature on triangle mesh? Then how can we define conformal metric deformation on the triangle mesh? Then the third part is very difficult. Then basically, the remaining metric just a triangle edge length. So basically, we have triangle mesh. Each edge has a length. Then all the edge lengths give you the remaining metric. So it's pretty straightforward. Okay. Then basically, for each triangle, 3 edge lengths satisfy triangular inequality. So this is the requirement for discrete metric. How do we define Gaussian curvature? So we use something called angle deficit. So given a vertex, which is in the interior of triangle mesh, then we count the surrounding angles. Then the 2 pi minus summation of surrounding angles is defined as a Gaussian curvature at this vertex. Then how can we define the Gaussian curvature, geodesic curvature on the boundary? Basically, which is a pi minus surrounding angles along the boundary. Okay, so that's the definition. Then we can prove the discrete Gauss-Bonnet, the total Gaussian curvature still satisfy this formula. Okay. Then in one of our recent work, we prove that if the triangulation is good, then the discrete Gaussian curvature converge to the smooth Gaussian curvature. That the convergence rate is linear, meaning the error is bounded by a constant multiply the diameter of the triangles. Okay, so this gives us a faithful approximation for the curvature. Now we know that in smooth case, the Gaussian curvature is determined by the remaining metric. Then in discrete case, this is very simple. This is just cosine law, meaning if we have a Euclidean triangle, if we know 3 edge lengths, we can determine the 3 angles. And the relation between the angles and the edge lengths is given by the cosine law. Then, so if each triangle is a hyperbolic triangle, then we can still determine the inner angles from their edge lengths. Okay, for a spherical triangle, we have spherical triangle cosine law as well. So therefore, the Gauss theorem is very simple in discrete case. Define the deformation, conformal metric deformation is more tricky, and this is the key actually. So we know that in smooth case, we conformally deform this surface to the plane. Then this deformation is conformal if and only if we map infinitesimal circles to infinitesimal circles. Then in discrete case, we replace infinitesimal circles to finite circles. Okay, what does that mean? So then this figure shows the key idea. Then this idea was invented by Thurston. Okay, we know Poincare conjecture is a special case of Thurston conjecture. So suppose we have a planar domain, okay, here. Then we compute a triangulation on the planar domain. Then we put a circle on each vertex. So here we have many circles, okay, on the triangulation. Then all the circles are tangent to each other. Then we deform the circle radius, okay. For example, we deform this circle to this one. The radius has been changed. But we do not change the combinatorial structure, okay, or the triangulation. We do not change the tangential relation among all the circles. So therefore, by deforming the circles, we deform the underlying triangulation from this one to this one. Okay? So then you'll see the domain here, the triangulation defined domain here, deform to the triangulation domain here. Okay? Then Thurston conjectured that if we refine triangulation, okay, make the triangulation refiner and refiner, then this kind of mapping will converge. This piecewise linear mapping between triangulations will converge to the real conformal mapping. Okay, so that's the intuition. Because conformal mapping maps circles to circles, so therefore we just map circle to circles. But we change the size of circle, but do not change the relation among circles. Then this conjecture was proven by Sullivan, the mathematics department chair in the Stony Brook, who got a Wolf medal last year. So this gave us the idea. Using the circle packing, we can approximate the conformal metric deformation. So this is the key to the whole computation. Okay. So then if you think this is intuitive, this is natural, then everything can be deduced from this intuition. Okay. Okay, then let's follow Thurston's construction. We have a triangle, then we put 3 circles at the vertices. Then the circle has an intersection angle, okay? Phi 2, 3, phi 1, 2, phi 3, 1. Then we can deform the circle radii, okay? But we do not change the circle intersection angle, okay? Then the edge length, okay, is given by the circle radii, also the intersection angle by this formula. Then we can change circle radii, but keep this one to be constant, okay? Then we can define a conformal factor to be the logarithm of the circle radius, okay? Then by direct computation, we can prove the following. The first, if we change circle radii, the Gaussian curvature will change. Then the Gaussian curvature change satisfies this symmetry condition, okay? Then the infinitesimal change of Gaussian curvature, infinitesimal change conformal factor satisfy this Laplace equation. Here, delta is a discrete Laplacian. Okay. Then we can define curvature flow. So this curvature flow is in the exact same form as a smooth case. We change, okay, the conformal factor proportional to the difference between current Gaussian curvature and the target Gaussian curvature. Okay. By using this flow, basically we can reach, okay, the desired metric. Then we know that Perelman see through this flow, and he proved that actually Ricci flow is a gradient flow of some energy, something called entropy energy, and this energy is convex. So in this case, we can still prove that this flow is the gradient flow for this energy, and this energy is convex. So therefore, computing this flow is equivalent to minimize this energy. Because convexity of this energy, then we can use Newton's method to compute it very efficiently. Okay, the Heisen matrix can be written down explicitly. So that's the theoretic framework. Okay, so basically this is the original Ricci flow. Okay, then using Perelman's work, we can show this is the gradient flow for this energy. This energy is convex. We minimize this energy. Okay.
It's obvious it's convex.
No. Require a lot of proof. Yeah, I will go through the proof. Okay. Yeah. Then yeah, it's highly non-trivial, I should say, especially for 3-dimensional case. Yeah. Then the key point is that the convexity of this energy, then the convexity for the configuration space for all the possible conformal factors. Okay, this is also critical. Yeah. Then from those two, we can prove the admissible closure space. Yeah. Then we will show that the mapping between the U space and the closure space is 1-to-1. Okay. Then let's go through that. Then everything comes from cosine law. So therefore, without using too much advanced mathematics, we can do everything. Suppose we have a Euclidean triangle. Then we have 3 edge lengths. We have 3 angles. Then we consider the angles as a function or edge length. Then we calculate the partial derivative of theta I with respect to Li. So this theta I, this Li. Then we get this formula just by cosine law directly. Okay. Then similarly, we calculate the partial derivative of theta I with respect to the edge length Lj. Okay, theta I, Lj here. Then here we get a formula here. Then if we replace the edge length using the circle radii, okay, then we can get the partial derivative, this one. Okay, the edge length Li with respect to gamma j, Rj, we get a partial derivative here. So everything is an explicit computation. Then we pack everything together. Basically, we get the relation, differential relation between the angles and the circle radii. Okay, conformal factor here. So we can write down this one explicitly. Okay. Then this formula looks very complicated, but in fact, it has a very simple geometric interpretation, which can be proven as well. So then this is the result. So basically, suppose we have 3 circles, okay, 3 black circles. There exists a unique circle, the red one, which is orthogonal to all 3 black circles, okay, the red one. Then the center, this circle is called a power circle. The red circle is power circle. The center of power circle is called a power center. Then from power center to each edge, we define that as H. So Hi, okay, Hj, and Hk. Then basically, the partial derivative of this angle with respect to this circle, okay, equal to Hk here divided by Lk. Okay. And basically, the partial derivative of this angle with respect to conformal factor of this circle equal to this height, okay, divided by this length. Okay, that's this formula. And similarly, the partial derivative of this angle, okay, with respect to this circle equal to the same Hk divided by Lk. So which is very geometric, very easy to memorize. Then this fact is very, very crucial. Basically, theta I with respect to Uj equal to theta j with respect to Ui. Okay, so this shows the symmetry. Okay, so here we give you the detailed proof. So you can go through that. I assume you have the PowerPoint, you have the slides. Okay. And basically, then we can define this differential form. Okay, theta I dui plus theta j duj plus theta k duk. And basically, you calculate the exterior derivative of this differential form. Okay, by direct calculation, you get 0. Okay, so this means that this differential form is a closed one form. Okay. Then here we show that we consider all the possible u, okay, ui, uj, uk. Then basically we show that for arbitrary ui, uj, uk, you get a valid metric. Okay, the triangle inequality holds. So then this means that the U space is equal to R3. So then this means that you have a closed one form in R3. R3 is simply connected. So therefore, closed one form is exact, meaning this one must be the gradient of something. Okay, then we can integrate this one. Okay, we get the energy. So that's the proof. Okay, so the symmetry is very important. Then basically, we define the energy this way. Okay, omega, as we defined before, from now 0, 0, 0 to U1, U2, U3. So this gives you the convex energy. Okay. Then we can calculate the Hessian matrix of this energy. Then from definition, we can determine the off-diagonal terms. Then basically, because theta 1 plus theta 2 plus theta 3 equal to pi all the time, so therefore, the diagonal element equal to the minus summation of other elements in the same row. Okay, basically with this format. So then you'll see that all the off diagonals are negative, and the summation for each row is a 0. So therefore, this matrix is a diagonal dominant. Then this one is a semi-positive definite. Then from here, we show the convexity of the energy. Then we generalize this to a triangle mesh. For each triangle, we define this energy. For the whole triangle mesh, we just add all the energies together. Okay, so therefore, we define a differential one form omega equal to summation go through all the vertices. Then the Gaussian curvature, multiply dOI. So this is the one form. Integrating this one form, then we get the energy. Okay. Then similarly, we can prove that this energy, is convex. Then we try to show that the mapping is unique. What does that mean? This means that give you arbitrary desired Gaussian curvature, there exists a unique metric which realize the curvature, meaning that the mapping from curvature to the metric is one-to-one. Okay, so it's possible that for general case, two different remaining metric produce the same Gaussian curvature. Okay, but if we require the mapping that the metric is a conformal, then each curvature uniquely determine a metric. Okay, then how can we prove that? So here we use some lemma. Suppose omega is a convex Euclidean domain. Okay, then f is a function defined on this Euclidean domain. Then f is strictly convex. Then the gradient map for each x, we map x to the gradient of x. Then this mapping is one-to-one. Okay, then based on this lemma, we can show the mapping from curvature to metric is one-to-one. Okay, as shown here, you have a convex planar domain. Then you define a convex function here. Then for arbitrary point x, then you can compute the gradient of x. Then the mapping from x to gradient x is one-to-one. Okay. Then in our case, so we have this energy. Okay, this energy is convex. Then the gradient of this energy equal to the Gaussian curvature. So therefore, the mapping from u vector to the curvature vector is one-to-one. The u vector represents the discrete remaining metric, and the k represents the discrete curvature. Okay, so then this shows if the solution exists, then the solution is unique. Okay, but the existence is really hard. So basically, you give me arbitrary Gaussian curvature, then whether there exists a remaining metric realize this Gaussian curvature, that problem is hard. Okay, existence is hard. For some special case, this has been proven, but in general, it's not. Yeah. Okay. Then this configuration is a substance circle packing. We put 3 circles, at each vertex with the intersection angle. The intersection angles to be acute. Then this can be generalized to other configuration. So this is the one used for theoretic proof. Basically, all the circles are tangent to each other. Okay, this was introduced by Jessica and basically here we see 3 circles. Then they are separated from each other. Okay, they do not touch, do not intersect. Then we can still define the power circle. All the series holds. So then the edge length given by this formula. So here 8 is a constant greater than 1. Then this 8 is called inversive distance. Okay. Then during the deformation, we keep this 8 doesn't change. Okay, but only change the circle radii. So then this still gives us the discrete curvature flow. Okay. Then later Feng Luo introduced something called a Yamabe flow. So in this case, the edge length is only given by 8 multiply the circle radii. And intuitively, here the vertex circles shrink to a point. Then the power circle goes through all 3 vertices. We can also treat the circle radii as an imaginary number. So therefore, the edge length is given by this formula. So here 8 is a constant. Then we can still define the power circle. Okay. Okay, then all the series holds there. Okay, then we can mix all the schemes together. Okay, some part is a system conventional, some part is a Yamabe flow, and this vertex is a imaginary circle radii. So therefore, this gives us a lot of flexibility. Okay. What's the meaning for the energy? The energy has a very special meaning, which is very mysterious. Let me try to explain here. So here, so this is R3. Okay, this is upper space. Okay, so this is the XY plane. Then the upper space actually is a three-dimensional hyperbolic space, H3. We treat the upper space as a three-dimensional hyperbolic space. Then through this triangle, we put this configuration on the floor. Through this triangle, we build a prism, okay, the green prism. Then through each circle, we draw a hemisphere. So we know that the hemisphere here means a hyperbolic plane. So basically, we use a hyperbolic plane to cut this prism. Okay. Also for power circle, we cut. So there are 4 hyperbolic planes cut this prism. Okay. We get this shape. Then the energy we just discussed actually equal to the volume of this prism, truncated prism. Okay. So that's the geometric meaning for the energy. Then here is a tangential circle packing case. We put this triangle here and build a prism, okay, and then cut the prism using a hyperbolic plane. Then we get this shape. Then the volume of this shape gave us the energy. Okay. Then here, this inversive distance. Okay, we can repeat the same story. Okay. Then it's very interesting that we built the energy purely from algebra. But then later, this was discovered. Then is there any intrinsic interpretation, or is a small part of a big picture, is unknown so far. And whether we can generalize this figure to higher dimension is unknown. Yeah. So this is an imaginary circle radii case. Okay. Okay. Then now we can give the details for this method. Basically, we try to minimize this energy. Okay. So here, U1, U2, U1 are the logarithm of circle radii at each vertex. Then the K bar is the desired Gaussian curvature for each vertex. Then K is the current Gaussian curvature. Then this is the energy form. Then the gradient of this energy is the difference between the target curvature and the current curvature. The Heisen, okay, is given by this form, which is diagonal dominant. Okay, if there is one edge, then we have an edge weight there. Then the diagonal equal to the summation for the off-diagonal elements. Okay. Then the computational method is as follows. So suppose we are given a triangle mesh. Then we compute the initial circle packing metric. Mainly, we determine the circle radii for each vertex. Then we determine the intersection angle for each edge. Okay. Then we define the target curvature Ki bar for each vertex. Okay, depends on our application. Then we can compute from the circle radii. We can compute the edge length. From edge length, we're using cosine law compute current Gaussian curvature. Then we compute the power circle, the circle orthogonal to 3 vertex circles. Then from power circle, we can compute the Heisen matrix. Then we solve this linear system. Okay, this is Newton's method. Okay, then we update. Okay, the vertex radii. Then we repeat step 2 through step 7. So basically, this is a convex minimization problem. Okay, then until we reach the desired Gaussian curvature. Okay, so this is a typical convex optimization, but it involves some combinatorics. Okay. Okay. So if you read the source code online, you will see this very clearly. Now let me explain how we compute auto mappings. So suppose here we have a human face, okay, represented as a triangle mesh. Then on the boundary, we choose 4 points, okay, P1, P2, P3, P4. Then we set the target curvature. So the target curvature for each interior vertex to be 0, yeah, because it's a flat interior, right? Then we want to map this curve on the boundary P1 to P2 to be a straight line. So this means the geodesic curvature on here must be 0. Okay, but then the the curvature at the corners are communicated. So this point map to here. Then the Gaussian curvature for this point is a pi over 2. Okay. Then the Gaussian curvature, the target Gaussian curvature for P2 is a pi over 2. Okay. And this point is pi over 2. This point is pi over 2. So basically, the target curvature to be 0 everywhere, okay, except those 4 corners, where the curvature to be pi over 2. Then we run Ricci flow, we get this mapping. So after Ricci flow, you get a metric with edge length. Then you can flatten one triangle. Okay, you know 3 edge lengths. You can realize that triangle on the plane. Then you can realize the neighboring triangle 1 by 1, 1 by 1, 1 by 1. Yeah, because the curvature equal to 0, then you can flatten the whole surface coherently onto the 2D plane. So that's the whole process. Okay. Then here we show the same surface. Okay, but we change configuration for the 4 corner vertices. Okay, the same target vertex, target curvature. Then you'll see we get a different, okay, rectangle here. Okay, then the aspect ratio of this rectangle is the conformal module. Okay, conformal invariance. So then this means that there doesn't exist a conformal mapping from this surface to this surface, such that we map P1 here to P1 here, P2 here to P2 here, P3 here to P3 here, P4 here to P4 here. Okay, so then this gives you the concept for conformal module and the conformal equivalence. Then you can imagine by changing this one, we can go through all possible rectangles. Therefore, the dimension for the shape space, okay, well, this kind of configuration is one-dimensional. Okay, that's the tetrahedral space. Then how about the annulus? So here we have a human face. Okay, then we remove the mouth. Then we set the target curvature to be 0 for the interior vertex. Okay, then we set the target curvature to be 0 on the boundary as well. Okay, let me explain here. So here you have an input surface, okay? Then you set the k bar equal to 0 everywhere. Then you find an arbitrary cut. You find a cut here. This is gamma. Then after running a Ricci flow, okay, you can map this guy to the planar strip. Okay, that one showing here. This boundary map to this boundary map to this boundary. Okay. Then you do another mapping, e power z or iz. Then this guy will be mapped to this shape. Okay. This one comes here. So this is the process to compute this configuration. And here you'll see that for the same human face, okay, same human face, but with a different expression, okay, we try to make the boundary as consistent as possible. Then when you conformally map to planar annulus, you'll see those 2 annulus are very different, okay? So this means that you cannot find a conformal map this guy to this guy. So therefore, this shows the expression change, okay, is not conformal, okay, in general. Why? Yeah, because you stretch the muscle a lot. Then how can we compute Riemann mapping? Okay, suppose we have a G0 closed surface, G0 surface with a single boundary. Then we convert it to an annulus case. We find one point and punch a hole at that point. Then it becomes an annulus. Then we map the annulus onto the plane. We fill the hole. Then the mapping is not unique. They differ by a Mobius transformation. And here the Mobius transformation has a closed form, okay, which can be written down as a ei theta z minus z now 1 minus z now z. So here theta z now are 3 parameters. Okay. Then for G0 surface with multiple holes, like the one showing here, we can play the same trick. So basically, we set the target curvature to be 0 everywhere. Okay, everywhere. Then the target curvature on the boundary to be constant. Okay, why? Because circle means the geodesic curvature is constant. Okay, so then also we require that the total curvature for the inner boundaries must be minus 2 pi. Okay, and the total curvature for the exterior boundary must be positive 2 pi. And adding those conditions together, we can calculate the metric. Then we can realize this surface onto the 2D plane. Okay. Then here we show more complicated case. Suppose we want to verify whether there exists a conformal mapping between this face to this face, such that we map exterior boundary to exterior boundary, okay, and the interior boundary to interior boundary. Basically, you map them to the canonical domain, and see whether those two canonical domains can coincide. If they share the same circles, circle radii positions, if they are, then there exists conformal mapping between them. Otherwise, there's no such kind of conformal mapping. Okay. Then if you want to find a diffeomorphism between those two in R3, it's more complicated. But finding a diffeomorphism here is much easier. So this shows dimension reduction. Okay. Then how about genus 1 surface? So here we show a genus 1 surface. Then basically we set the target curvature to be 0 everywhere. Okay, everywhere. We run Ricci flow, then eventually we can compute a metric, meaning the edge length, such that the surface is flat everywhere. Okay. Then how can we realize this surface on a plane? So here I show we need to cut the surface. Okay. So basically that's the input surface. Okay. Then we find two cuts. One is A, one is B. Then using the flat metric, we can map the surface. Okay, this is A, this B, this A inverse, this B inverse. Then we get one period. Then we can make many copies of this period. Okay, which can tell the whole Euclidean plane. Okay, so that's how we build the figure here. Okay. Then suppose consider arbitrary loop on the surface here. Then this loop will be lifted to a path, okay, on the plane. So then this is very useful for a lot of computational topology tasks. For example, you want to verify whether two loops are homotopic, whether one loop can deform to the other. Basically, if you do here, that will simplify a lot. Okay. Then this one, actually, this is a costar minimal surface. Okay. So this surface is a costar. So this surface actually saw a very long-standing conjecture in differential geometry. People try to see whether in R3 there exists some kind of minimal surface which has a non-trivial topology. Then costar actually he imagined this kind of surface and using computer to build part of this kind of surface and prove the conjecture in 1980s. Then this is a breakthrough in minimal surface theory. Actually, it's hard to see. This one has one handle and three boundaries. Then we set the target curvature to be 0 everywhere, and the target curvature to be constant along the boundary. Total curvature along each boundary equal to minus 2 pi. We can find the metric here. Then flatten it, get one period, and repeat this. Then for high genus case, it's more complicated. But so this is an input genus 2 surface. We need to find this kind of loops we see here. There are 4 loops, which are called fundamental group generators. Then we calculate a hyperbolic metric using a hyperbolic Ricci flow. Basically, we change cosine law to be hyperbolic cosine law. Then we flatten triangle by triangle, okay, onto the Poincare disk. This is a H2 model, 2-dimensional hyperbolic space model. Okay, then we see the boundary. Okay, the boundary are mapped to this kind of curve. Okay, so this gives you one period. Then you can make copies of this period. Different copies, okay, differ by rigid motion in hyperbolic space. The rigid motion in hyperbolic space is just a Mobius transformation, share the same form. Then you can get this kind of configuration. You can repeat this infinite many to cover the whole H2. Okay. Then for high genus surface with boundary, we can repeat the process. The tricky part is that, so the total curvature for this boundary, okay, is unknown. So you cannot determine that before you compute it. Yeah, because here the curvature equal to -1. So then basically it's a hyperbolic, it's not Euclidean. So therefore the geodesic curvature integration of this whole is not equal to 2 pi. So then this part is unknown, so the whole process is nonlinear. We cannot finish, we cannot determine the target curvature at the beginning. So this makes things complicated. Then for this is a topological pans. Basically, we set the curvature to be 0 for the interior point. Then the geodesic curvature on the boundary to be 0. So that means we want to map, okay, all the boundaries to be a geodesic in hyperbolic space. Then you can find a unique hyperbolic metric for that. Then after that, you can calculate the hyperbolic length, okay, under canonical metric. Okay. Then how can we compute quasi-conformal map? So just now we show we're using Ricci flow, we can compute all possible conformal maps. Then if we have a general map, how can we handle that? Okay, so computing a general diffeomorphism equivalent to solve this Beltrami equation. So given the Beltrami coefficient, how can you find the diffeomorphism? So that's the problem, okay? Then this one can be converted to be a conformal map, okay? So therefore, using a previous method, we can compute this map. So the trick is that we construct a new Riemann metric. Okay, so here we show the trick. So basically, if we know Beltrami coefficients mu here, okay, then we construct a new Riemann metric. Okay, dz plus mu dz bar. This is a new Riemann metric. Then consider the same map phi under this new metric. Then this mapping become conformal. So this means that you want to compute a quasi-conformal map. By constructing a new Riemann metric, the quasi-conformal become conformal. Then you use the Ricci flow, you can solve this easily. So therefore, for arbitrary diffeomorphism, if we know mu, we can compute the mapping, okay, using Ricci flow. Okay, so here we show some examples, right? Multiply connected planar domain, okay? This is a conformal. We set mu equal to 0 everywhere. So then this is a quasi-conformal. Then this is the one we showed just now. So here we decide the mu normal. We map this one to this one. So you see here, the greater the normal is, then the more distortion it introduced locally. But here you see that the normal, when the normal close to 0, the mapping is very close to be conformal. Okay, so therefore, by using mu, you have very refined control for the mapping. Okay, you know the distortion. Then it's very mysterious for us why the mapping from retina to brain cortex surface is a conformal. Why not general diffeomorphism? Okay, so then in summary, in this lecture, we show the theory for discrete surface Ricci flow. Then we gave you the computational method for discrete Ricci flow. The application using this method to compute surface uniformization. Okay, thank you.